everybody. Back to our final in-person lecture. I hope everybody's had a good semester. I'm sure it's a very busy time for most people if you have projects or finals coming up. Our final exam is on the last day of the exam schedule, which is April 22nd. And so you have lots of time to get ready for that. Much like for the midterms, I'm going to post some study materials for the final exam. So I'll definitely post. So the final exam is cumulative. It covers everything. But I'll post a detailed topic list like I did for the midterms and some practice problems. And I'll try to get those out before we get too close to the exam. And as I mentioned last time, there's a final assignment which you can do for bonus points if you want. If you do the assignment, I'll take the best 4 out of the 5 homeworks. The homeworks are being graded, even though that probably sounds like it's a lie, but I am working on them. I was working on them this morning. And today what we're going to do is we're going to try to get to the end of surface gravity waves if we can. And if I don't quite get there, where we missed a class on last week, I'll post a half-an-hour video or something to finish off the last topic if necessary. Before I jump into the review, does anyone have any questions about anything related to the course or the final exam or anything? Okay. And again, I'll post instructions and stuff for the final exam in terms of calculator and that sort of thing. Okay, so this is, I think, definitely the most equation-filled the review board has been so far. And that's because we're studying surface gravity waves, and surface gravity waves are a little bit more, mathematically complicated, just slightly, than sound waves. And one of the reasons is that sound waves we were able to look at just along the line. We just considered the flow as depending on x and the time. And we didn't have to worry about the other 2 spatial dimensions, y and z. But for surface gravity waves, because they're surface waves, there are fundamentally 2 dimensions involved. There's the direction of propagation of the wave, so the moving of the crests in, say, the x direction. And then there's the bobbing up and down of the surface, and that's happening in the z direction. So to study surface waves, we have to include at least 2 directions of motion. And so we're going to do it in x and z, and we're going to just pretend that y doesn't exist, basically. You can also think of it as what we're modeling is a wave where it's propagating in the x direction, but the crests are infinitely long in the y direction. If you just imagine you take a wave and just extend it infinitely, so that there's no dependence of the wave on the y direction, that's equivalent to the analysis that we're doing. And so, even though this is 2-dimensional, this is physically realizable. You can actually make waves that have these properties. For example, using a wave tank, you can make these kinds of waves. And so we basically are working through the fundamental equations of fluid dynamics that we've been using for this whole course. As we wrote out last time, the momentum equation in x and the momentum equation in z. And these have the usual terms. We've got our time derivative, we've got our vective terms, u dot grad, or u du dx, w du dz, our pressure gradient force. And then we introduced a new element to study surface gravity waves, which is the gravity force. And so that shows up as this minus g on the right-hand side of the w equation. So it's very important that this g term, which is the gravitational acceleration, it only enters into the z equation, which is the w equation. There's no corresponding term in u because gravity only acts in the vertical, of course. And then we have the continuity equation, and when we used sound waves, we studied the full continuity equation, which had the material derivative of density and all that stuff. But here, the key thing that we've done is we've set the density as a constant. So we're saying rho, the density, equals rho naught, which is the constant density, which is constant in time. And so that causes this simplification. Basically, the mass continuity equation collapses into this very simple equation, du dx plus dw dz equals 0. And this is also called the incompressibility condition, because what it basically reflects physically is that for sound waves in air, the compressibility of the air is very important. So as a sound wave propagates through air, all the little parcels there are kind of getting squished and expanding over and over and over at a very high frequency. And they're getting squished by pressure forces, basically. But water is very close to being incompressible. You can compress it a tiny amount by squeezing it, but really very, very little. And so we set the density to constant, and if the fluid cannot be compressed, then you can never have a velocity that squeezes in from all sides, because that would cause compression. And what happens is if you try to set up such a flow, the incompressibility resists that, and it creates this pressure force that eradicates that kind of velocity field. So this is called the incompressibility condition, or also sometimes called the divergence-free condition, because this is equivalent to writing the divergence of u equals 0. Okay, so these are our equations of motion. But we mentioned last time that again, unlike sound waves, surface waves are associated with the surface, and so the physics of what happens at that surface is very important. And that contributes two extra equations which are called boundary conditions. And if you've taken a math course like 2260 differential equations, you would have done some differential equation solutions that have boundary conditions. And this is much the same, except that we're applying it to partial differential equations rather than the ordinary differential equations that you study in that course. But boundary conditions are sort of a mathematical theme that extends across all sorts of different kinds of differential equations. So last time, we wrote down two different boundary conditions, one of which is pretty simple to think about, and the other one which is a little bit more complicated. So I'm going to start with the bottom one, and this is the pressure condition. And I'll just redraw the schematic here. So the schematic of our system is we have z equals 0 is what the surface would be if there was no waves, and then we have a surface that actually fluctuates relative to that, and the height at any point above the surface is called eta of x and t. So here's our x direction, here's our z direction, and then eta is the height at the position x and the time t of this free surface at the top. So really, so our surface is defined by z equals eta of x and t. And this is the Greek letter eta. It's kind of like a stretched out lowercase m. I remember one time I was in a math class, and there's this other Greek letter called psi or xi, and this basically looks like this. And I had a professor who basically drew this as this. And they would write integrals with respect to this. So they had like f of this equals the integral d this of, or say f of maybe z, equals the integral of f of z and this. And I was like, are you literally just squiggling on the board? Like, is that a real, I had no idea. And eventually just had really bad handwriting, and this was supposed to be the Greek letter C. Anyway, but eta is not quite so bad. But in physics, you often run out of the Greek letters, so you end up using the obscure ones that you might not want to use. So anyway, so eta, that's our free surface. And so the surface is defined by the vertical level equals this particular function eta. And then eta is going to change in space and time as the waves propagate and bounce up and down. Okay, so the simplest boundary condition of the two, the simpler of the two, is the pressure condition. And what this says is that at the very surface of the water, which is z equals eta, then the pressure has to equal the atmospheric pressure. And that's because the atmospheric pressure is pushing down on the surface, and so the water has to create a pressure that balances that. Otherwise, there'll be a pressure jump as you go from the atmosphere to the ocean, which would create a very strong force. And as it turns out, you can have a jump like that if you're accounting for surface tension. So surface tension can support those kinds of jumps. And you may have encountered, has anyone encountered pressure jumps in bubbles at any point, maybe in a thermodynamics course or fluids course? It's called the Laplace condition. Okay, maybe not. So anyway, so the water does have this surface tension, but it's not important for these surface waves. So anyway, so we're going to ignore surface tension, and what that means is that there can't be a pressure jump, and so the pressure, the atmospheric pressure in the air has to equal the water pressure right at the surface. So mathematically, we say that the pressure field at any point x, at any time t, and at the particular height, z equals eta, which is right at the surface, then we have to have the pressure equals the atmospheric pressure. And atmospheric pressure here is just treated as a constant. So you could also say, well, what about the fact that there's high and low pressure systems, weather systems flowing over the top? And if you wanted to treat that carefully, then the right-hand side would be a function of time and space. And you could incorporate that, but that's a pretty weak effect because the atmospheric pressure doesn't vary that much. Okay, and then the more complex condition is the top one. So that's just called the pressure condition. And the first one I wrote down is called the kinematic surface condition. And what this says is that basically if you have parcels, so here's our surface, here's our z equals 0, that if you have a parcel of fluid that's sitting right on the surface, that this parcel sort of moves with the surface, and in some way it determines the motion of the surface. So for example, if this surface is going to move downward, so that at the next moment maybe our wave looks like this. So this surface part here, if you just dye this red, this is now red, so we have moved down here. And so if that's the case, that if the surface has dropped down, then it stands to reason that this parcel has had a downward velocity, right? Whatever parcel's at the surface must be moving with the surface. And so we wrote down the condition that at the surface, z equals eta. And then because we're thinking about parcel motion, we can just take the d by dt, the material derivative of this, and then we end up with d by dz of z, d by dt of z is just w, and you get w equals d eta dt. And then this is just that equation written out in very explicit language. So it says that the velocity right at the surface, so at a point x and a time t, and right at the level z equals eta, so right at the surface. So we're talking about the velocity, the fluid velocity right at the surface, that velocity has to match how the surface is actually changing, whether it's going up or whether it's going down. And that turns out to have two components. You have d eta dt, so this is just the time derivative part. So if d eta dt is positive, so if d eta dt is positive, that means the height is increasing, so that means the height is going up. And so that would mean you would have a w which is positive, which is a positive vertical velocity on the left-hand side. So when you have a rising surface, you have an upward velocity. That makes sense? But because the surface also moves from side to side, the vertical and horizontal motions kind of get mixed, especially if you imagine the surface has a slope to it. Then that can kind of mix horizontal and vertical motion. And so then we get the second term here, the horizontal velocity u times d eta dx is the x component. But luckily, these pressure and kinematic conditions are pretty complicated. They're called nonlinear because the variables that we're trying to figure out, we're trying to solve for, if we want to compute how this wave is going to move, we want to compute eta prime. We want to see how, we want to make a formula for like how is the surface going to move over time. But that eta function is inside the argument of u. And it's inside the argument of w. You're evaluating w at this point eta. So like the solution is kind of stuffed inside itself. And you're evaluating variables at the solution of its own system. And so mathematically, this is kind of a mess, although it can be handled on the computer. So you can just take this exact equation, solve it on a computer, and you get what are called nonlinear waves. What we're going to do is do the classical problem of studying linear waves. So as long as the waves are small amplitude, which basically means that eta divided by the depth of the ocean is a very small number, which is true for basically all waves that are driven by wind, then we can do the linearization process. And so that's the right-hand side. So we started that last time. So whenever we linearize, we always do the same thing. We always have to linearize relative to some background state. So whenever you linearize, it's always relative to something. You can't just linearize in general. It has to be relative to some particular background state. And in this case, we've chosen the state of rest. So we've written u equals u naught plus u prime, and w equals w naught plus w prime. But because we want the basic state of the ocean upon which waves are going to fluctuate, because we want that to be the state of rest, we set u naught and w naught equals 0. And that will correspond to a flat surface. So we just have the sort of very boring situation of here's the surface, and then there's no velocity inside. So flat surface, and no velocity inside. And then we also, I should mention, we also made the approximation that we're infinitely deep. And that's something I talked about last time because we want to study the deep water waves. It turns out the surface gravity waves, they behave very differently in shallow water versus deep water. We're doing the deep water case, and so we're just going to take the extreme case of that, where the ocean is infinitely deep. And so that's our basic states. So U naught is the basic state, W naught, they're both 0. And then for our eta, our surface height, we're going to say that the background is 0. You could actually imagine, having a situation where, let's say you have some land. This is imagined land, and let's say there's ice on the land. So like, let's imagine this is, say, down by Antarctica. It turns out that when you have very, very heavy ice sheets, the gravity of the ice sheet actually pulls the ocean toward the ice. So rather than the ocean being flat like this, it's actually kind of pulled up a little bit towards the ice. And so you can imagine, if you wanted to look at waves on top of this, you might want to have eta, the background free surface, be some kind of sloping surface. But again, that's a special case. We're not going to deal with that. But just to give some idea of how this could be extended or what other types of problems you could do. But we're going to do the simplest traditional case of a flat surface with no velocity in the interior. By the way, let's mention about this. This turns out to be very interesting because everybody basically knows that when you have climate change and the temperature goes up, you melt the ice cap to some degree, right? And so you melt this ice, and so the ice melts and it flows into the ocean and it raises the sea level. But the sea level doesn't go up uniformly. It doesn't go up the same amount everywhere. And actually, if you melted Antarctica, the sea level near Antarctica would actually drop. It would go down because this gravitational effect gets eliminated and this water kind of flows back out. But it would go up a lot everywhere else. Anyway, that's not related to surface gravity waves. Okay, so we have eta naught is 0. We're going to consider a flat surface. And now P naught is the very interesting part. So the pressure, when you have a flat surface like this, the pressure isn't constant. So when we talked about sound waves, we said, well, we're going to have some background pressure, which was usually 1 atmosphere, and a background density. And that was just constant. But in the ocean, the pressure increases. So P increases as we go down. And you can almost imagine that you put like a little scale here, and then there's a column of water sitting on that scale. And then the pressure is kind of the weight of the column. So as you bring that scale down in the water, there's more water on top of it, and so your pressure goes up. And so we derived last time this equation called the hydrostatic relation, which says that the rate of change in the vertical of the background pressure is just equal to minus rho naught times g. And you can integrate this to get a formula for P naught of g, and we get this formula P naught of z, the background pressure as a function of depth, equals the atmospheric pressure minus rho naught gz. And if you recall that in this course, we always say z is less than 0 if you're inside the ocean. So like we have, like the bottom is like negative 4,000 meters would be the bottom of the ocean. And so then because this z is negative, that means that this whole contribution is positive. So as you go to deeper and deeper depths, the pressure is going to increase. And then the last thing that we did last class was we basically stuffed these assumptions of every variable equals a 0 part, a naught part, plus a prime, P naught plus P prime. We put that into our equations of motion, which were our momentum and continuity equations. And we derived the linearized equations of motion, which are these three. Of our linearized U momentum, linearized W momentum, and linearized continuity or incompressibility condition. And so what we're going to do now, so we've done basically, so when we set up our system, we had 3 equations, and then we had 2 boundary conditions. And so we need to linearize everything. And so we've linearized the 3 equations, and so the next step is to linearize the boundary conditions, and then we'll see what we get from there, and it turns out we'll get very nice formulas describing surface gravity waves. Okay, so I'll just pause there after that fairly long review. Does anyone have any questions about what we covered last time, or anything about the review, or there were a few questions about notation last time? Does anyone have any questions? Okay. All right. And the nice thing about linearization is it always makes your equations much simpler. And so we've already seen this with our momentum equations. We have these nonlinear terms have dropped out because they ended up having 2 primes. But the linearization is going to make a major impact on how we can understand and apply these boundary conditions. Okay, so the next step is linearizing the boundary conditions. So let's start with the kinematic condition. So we start with W of x, z equals eta of x and t, and time equals the eta dt plus u of x, z equals eta time the eta dx. Okay. So we're going to put in u equals 0 plus u prime, and eta equals 0 plus eta prime, and w equals 0 plus w prime. So what do we get from that? So on the left-hand side, so w gives us 0 plus w prime evaluated at x, and then z equals eta prime of x and t, and that will equal partial eta prime partial t plus u of x, z equals eta prime and t d eta prime dx. Okay. So to make progress here, we want to get these etas outside. Right now they're inside the arguments sorry, this is a u prime here. They're inside the arguments of the velocity, the w velocity here, and the u velocity here. And we can get them outside by using Taylor's theorem. So whenever we do linearization, we often end up invoking Taylor's theorem. And so I'm going to write here w prime of x and eta prime and t is equal to w prime of x and 0 and t. So basically we're going to expand. We're saying eta prime is a small number, so it's close to 0. That the surface is undulating, but it's close to being flat. That's the small amplitude assumption. So essentially we're using here that eta prime is almost 0, but not quite. So our w prime evaluated at eta is equal to our w prime evaluated at 0 plus the Taylor series term, which is eta prime times dw prime dz. So this is the first order correction. First order Taylor series. And so it kind of makes sense that the velocity right at the surface is equal to the velocity of where the surface would be if it was flat, plus another little tiny bit that corrects it. But we are lucky in that this second term here, eta prime times dw prime dz, this term here has 2 primes. So we drop them. We drop during linearization. So, to a good approximation, this roughly equals just w prime of x, z equals 0, and t. And so our Taylor's theorem result, just to write it down one more time clearly, that it's very difficult mathematically to think of what's happening right at the surface as the surface is moving around in maybe a complicated way. But when we're linearizing, because the surface is only moving a little bit, we can almost like treat it as flat for the purpose of this equation. And to first order accuracy, dropping these 2 prime terms, which are obviously doubly small compared to the individual primes, we just get this simplified expression that W prime at the surface is very close to W prime, what it would be at the flat surface. Okay. So that's this term. We dealt with this term so far. Eta prime, well, there's nothing we're really going to do with that one. So now let's look at. So this I'll write here. This is the left hand side. And now let's look at the right hand side. So our right hand side is the eta prime dt plus u prime x z equals eta t d eta prime dx. And then now here we have the same thing as before. We have a velocity evaluated at exactly the surface, and we can use Taylor's theorem again. So I'll write Taylor u prime of x z equals eta prime t equals u prime x z equals 0 and t plus eta prime du prime dz. And again, this term has 2 primes. And so we draw. And so, as before, we get u prime of x and z equals eta prime and t is roughly equal to, and it's a good approximation for linear waves, z equals 0 and t. And so there's a little bit of sort of Taylor series trickery coming in here. But really all we're saying is that when we're applying these boundary conditions, because the fluctuations of the surface are assumed to be small, then mathematically it's a good approximation to just treat the surface as flat when we're applying the boundary conditions. So we'll later actually calculate what the disturbance of the free surface is, and it won't be flat. But for this equation, it turns out that the deviations from flatness come in at double prime order. So they're very small in terms of their effect on the system. And so we can basically just approximate that away, and then we'll get an accurate description to first order of how these waves behave. And so our our linearized kinematic condition is W prime of x z equals 0 and t equals the eta prime dt plus u prime x z equals 0 and t times the eta prime dx. That's just we've taken this top equation and we've used, rather than evaluate u prime at eta, we're using Taylor's theorem to evaluate it at 0. But we're not quite done. There's just one more step, which is just a simplifying step, that this second term, this whole second term now, even after we've simplified it, it still has 2 primes. And so we still have 2 primes here. So we can drop. And so our final linearized equation is just w prime at x, z equals 0, and t equals the eta prime dt, which is way, way, way simpler than what we started with. So this is now the linearized kinematic condition. And then looking at this equation, it's fairly, once you have derived it, not saying that it was obvious to begin with, but once you've derived it, it's fairly easy to interpret. Because it says that if the eta dt is positive, which means that the height of the surface is increasing, then there must be a positive vertical velocity that's carrying that surface upward. And then vice versa, if the eta dt is negative, that means the surface is falling, and that's got to be associated with a downward velocity. And so that just means that the motion of the fluid right at the top of our domain, right at the surface, has to be consistent with how the surface is moving. And that's really, really key to the physics of internal gravity waves. Because this is ultimately the condition that's gonna couple together or link together the motion of the fluid in the interior with the behavior of the surface. They're coupled through this equation, the kinematic equation of the surface. So that was the kinematic condition. We'll call this. I can't remember what the numbers were. But let's call it the kinematic condition. Okay, so our second one is the pressure condition. So our pressure condition was that P at x, z equals eta of x and T has to equal P atmosphere. Okay, and this is really eta. Okay, so for this one, again, we do the usual thing. We take all of our decompositions, u equals 0 plus u prime, p equals p naught plus p prime. We just plug them in here. So we'll recall here, p equals p naught of z plus p prime. And so we're saying here, p evaluated at this particular point, x, z equals eta prime, and t has to equal p atmospheric. So that means that, so p of x, z equals eta, and t is equal to, so our pressure has two components, is equal to our background pressure at z equals eta prime, plus our perturbation pressure at x, z equals eta prime, and t. And just as a reminder from last class, the background pressure depends only on depth. So you might imagine a situation where the pressure also depends on x, and that can happen especially in situations where the fluid is rotating, but we're not gonna deal with that here. But so as long as you have a flat surface, the pressure just increases as you go down, and it doesn't change side to side. So along any flat surface inside the ocean, the pressure is constant. So the P naught is a known formula. So P naught of z is equal to P atmospheric minus rho naught of gz. So what that means is that P naught of z equals eta prime is equal to P atmospheric minus rho naught g eta prime. So we have a known explicit formula for the background pressure, and so we're trying to evaluate the full pressure, including both the background piece and the perturbation piece, right at the surface, z equals eta prime, I forgot my prime there. And so we have to evaluate both pieces, both the perturbation piece and the background piece. And so when we just plug z equals eta prime into our formula, we get this expression here, P naught of z equals eta prime is the atmospheric piece minus rho naught g eta prime. And then for our perturbation piece, we can do our thing we did before, and we don't want to evaluate it right now. Z equals eta, we have eta is inside the argument of the p prime, and we want to get it outside, so we use Taylor's theorem. And we write p of x, z equals eta prime, and t equals p prime of x, z equals to 0, and t plus eta prime times dp prime dz. So this is just the same, we've done the same trick now 3 times. We're just saying, if we need to evaluate something right at the surface, we can basically evaluate it as if the surface was flat, but plus a correction term. But this term here has 2 primes. And so we drop it. And so we end up with p prime of x, z equals eta prime and t is roughly equal to p prime at x, z equals 0, and t. The vertical line here, these are 2 sort of separate pieces of analysis. So this part here pertains to the first term, we've simplified that. And then this part here pertains to the second term, we've simplified that. And this whole thing should equal P atmospheric. So this whole expression, the pressure evaluated at point x and time t and right at the surface, this should equal the atmospheric pressure. That's just consistency between the weight of the atmosphere pressing down and the water pressure right at the surface. So, rewriting this now, we get our two terms here, we get this term, P atmospheric minus rho naught G eta prime, plus this term here, P prime of x z equals 0 T equals P atmospheric. So the left-hand side here is the total pressure of the fluid that consists of a part coming from the background, the basic state, plus a part coming from the perturbations. And then the right-hand side equals the atmospheric pressure. But something nice has happened here in that the atmospheric pressure ends up on both sides of the equation. And so we can just cancel those out. And what we end up with is just rearranging. We get P prime of x z equals 0 and T equals rho naught G eta prime of x and T. And this is our linearized surface pressure condition. And this also makes sense when we think about it, because basically what it's saying is, so P prime at z equals 0. So let's go back to our diagram. So we have our z equals 0, and we've got our waves on top of that. And this point here, we could say we're going to look at, let's say this is x and z, so this is P prime of x, z equals 0, and T. So we're kind of asking the question here, what is the perturbation pressure, the pressure associated with the wave? Or like how much extra pressure do we have at this point than we otherwise would if the surface was flat? And the answer is that the amount of extra pressure we have is proportional to how high the wave is, which is eta, above that point. There's a certain amount, at any point where the free surface used to be, if you look at the pressure at that point, there's a wave over top. So there's a certain amount of extra water that's above that point, and that leads to an enhanced pressure. And so when we look at our formula, we see that the pressure at where the flat surface would normally be, that extra little bit of pressure we have, is equal to the density times gravity times the amount of free surface that's there. So if the surface is a little bit larger, if the surface is a bit higher, then eta prime will be larger, and then the pressure anomaly, or the little bit of extra pressure we have at this point, will be higher. And so that's the meaning of the linearized surface pressure condition. Okay, so summary. Full linearized system for surface gravity waves. We have equations, or equations of motion. We have du prime dt equals minus 1 over rho naught dp prime dx. We have dw prime dt equals minus 1 over rho naught dp prime dz. We have du prime dx plus dw prime dz equals 0. Then we have p prime at x, z equals 0, and t equals rho naught g eta prime of x and t. And we have w prime of x, z equals 0, and t equals partial eta prime partial t. And so this is our full system. And so now, our job is no longer deriving equations and using physics. We've basically done all the physical analysis here. We've used F equals ma, conservation of momentum. We used conservation of mass to get the incompressibility condition. We've used consistency of the two pressures, the air pressure and the water pressure. We've used consistency of the fluid motion with the fluid surface. And so we've used all those principles, those physical concepts, and linearization to derive a set of 5 equations. And now these turn out to be closed equations. And so now our job really becomes a mathematical one, that our job is now just to solve these equations and see what they actually predict. We've turned the physics into math, and now we want to solve the math, and that'll tell us about the physics. Okay. So I'll just give a minute to finish writing this down. So I'm just going to jot down basically just what I said. So this section is called solving the linearized surface gravity wave equations. So we have applied the principles of momentum conservation. Here's F equals ma. Mass conservation, which is del dot U equals 0. Pressure consistency. And surface movement consistency. We have turned these physical concepts into mathematical equations. Our next goal is to solve these equations. And see what they predict. So, let's go step 1. We're going to combine the two momentum equations. Two momentum equations and the mass continuity equation. So we have here partial u, partial t equals minus 1 over rho naught dt prime dx. So we're going to take, and we have also dw prime dt equals minus 1 over rho naught dp prime dz. So what we're going to do is we're going to take d by dx of this whole equation, and we're going to take d by dz of the bottom equation. Right? The x derivative of this top equation and the z derivative of the bottom equation. That's what we get. When we take the x derivative of this, we get d by dt of du prime dx equals negative 1 over rho naught d squared p prime dx squared. And when we take d by dz of this equation, we're going to get d by dt of dw prime dz equals minus 1 over rho naught d squared p prime dx squared. And the reason that we're doing this is that we know from mass continuity that du prime dx.
Is that x supposed to be a z in the bottom equation?
Yes, thank you. dz squared. Nice. So we know from mass continuity that du dx plus dw dz equals 0. And on the left-hand side, this equation has du dx, which is the first term. And this equation has dw dz, which is the second term. So if we just add these equations, then we'll end up with something that's going to be 0 from mass continuity. So I'm going to say add these equations. So what we end up with here is we get d by dt of du prime dx plus dw prime dz equals minus 1 over rho naught d squared p prime dx squared plus d squared p prime dz squared. And this thing in the brackets, we're taking the time derivative of du dx plus dw dz, but that thing is just 0 because our fluid is incompressible. So this thing internal to the time derivative, this just equals 0, and so the time derivative of 0 is still 0. And so we get d squared p prime dx squared plus d squared p prime dz squared equals 0. So now we've simplified this thing down to an equation in one variable. I'm just going to leave all 5 on the board here because we don't want to refer back to those, but I'm just going to delineate it by a red line here. Okay. I'll just give it a second. So when we studied sound waves, at a certain point we had boiled down a whole bunch of different equations into this one equation called the wave equation. And if you remember how we solved that, we solved it using an ansatz. We basically guessed the solution with some kind of cosine wave, and then we plugged that in, and we derived conditions on that wave that makes sure that it satisfies the equation. So here we're going to do a very similar thing. So we're going to solve using a wave ansatz. And an ansatz is just a guess. So we're going to guess that p prime of x, p prime of x, z, and t is equal to, what notation did I use? Is equal to sine of kx minus omega t This omega is different from W. So this is the angular frequency of the wave, and that's the wave number. So we have the wave number, the angular frequency. And so that's very much like, but there's more, I'm going to write another thing here. But so this is very much like what we did with sound waves. We have some kind of propagating wave. It's a sinusoid. You could also use a cosine. You could get the same answer. And so we're expecting it's going to be like a wave, a sinusoidal wave in the x direction. But it doesn't make sense to make a similar assumption for the depth direction, because we don't expect the thing to be a surface wave. We don't expect it to be wavy in the vertical. What we mostly expect is it's going to be concentrated near the surface, because surface waves should have basically all of their velocity, all of their structure should be near the surface, and as you go infinitely deep, you shouldn't see the wave anymore. It should basically die off. So I'm just going to leave this general, and then say we have some function capital P of z multiplied by this sine kx minus omega t. And this tells us, as we go up and down in the water column, what happens to the amplitude of this wave. And this thing has a name. This is called the vertical structure function. And as yet, this is unknown. So this is the idea of the ansatz. We're going to guess the form in k and in sort of x and time, and we're going to leave the behavior in z general. But then we plug this ansatz into our equation, and we see what that equation tells us. So we plug this into our equation. Okay, so we had d squared p prime dx squared plus d squared p prime dz squared equals 0, which implies d squared by dx squared of p of z sine kx minus omega t plus d squared by dz squared p of z sine kx minus omega t equals 0. And now, because we have an explicit formula, it's a guess. We don't have it. We don't have it fully worked out yet, but we have some kind of formula in terms of an explicit z, k, and zx and t dependence. We can start calculating these derivatives. So when we take two x derivatives of a sine, we get sine goes to cosine, and then cosine goes back to negative sine. So we get here negative p of z times, and there's a k squared that comes out because we take two chain rule derivatives, p of z times k squared times sine of kx minus omega t, plus the z derivative doesn't hit this sine part because it only depends on x and t, but it does hit the p part. So we get d squared p dz squared times sine of kx minus omega t equals 0. Okay. And again, I've used the ordinary derivative b here because p only depends on z. It doesn't depend on x or time. And then just like what happened when we did the analysis for the sound waves, our sine factors appear the same in both terms, and there's a 0 on the right-hand side, so we can cancel those out. And so we're left with an equation just for p, capital P. We get d squared of capital P dz squared equals k squared p of z. So, now this is another differential equation. So we started off with our differential equation in x and z. We put in an ansatz that had a wave-like form in the x direction and an arbitrary form in the vertical direction. And what we got was an equation, a differential equation in the vertical. And this basically constrains our vertical structure. So this is called the vertical structure. And it's is actually a pretty simple kind of differential equation. It's a second order equation. It's got two derivatives. That's kind of bad. You usually like to have it in first order. But it's got constant coefficients, because this k squared is just a constant here. So you have just a constant multiplying p on this side, and you have two derivatives on the left-hand side. Does anyone have a suggestion, has seen maybe an equation like this before? Does anyone have any idea how you might solve it mathematically?
Take a guess at the function being an exponential to the power of mz.
Yeah. And do you know what's the name of that method?
No.
I honestly don't even know what the power. I call it the method of the characteristic equation.
Right.
Ben's suggestion is correct. So we can solve this. So I'll say this equation. So this is a second order linear ordinary differential equation with constant coefficients. And so we can solve it using the characteristic equation, which is something that you may have forgotten, but it probably came up at some point in 2260. So basically, this is another ansatz. We use an ansatz that P of z is equal to a coefficient A times e to the RT. It's conventional to use R. You can use any other symbol you want. So basically, we're going to guess that the function P of z is an exponential, but the exponential constant that's in the exponential here, we're going to call it R. We don't know what R is yet. So we're going to take that ansatz, plug it into our vertical structure equation, and then that's actually going to tell us what the value of R has to be. So we plug in. So we get d squared by dz squared of a e to the RT equals k squared times a e to the RT. When we take two derivatives, this is just an exponential. So the derivative of an exponential is the same function back times the coefficient by the chain rule. So here we get a times r squared times e to the RT equals k squared times a times e to the RT. And whenever you have an ansatz, it's always nice if something cancels at the end. If nothing cancels, your ansatz usually wasn't good. But in this case, we have the a's on both sides, so we can cancel those a's. And we also have e to the RT on both sides, so we can cancel those. And so we just end up with r squared equals k squared, or taking the square root, r equals plus or minus k. And then that gives us our solution for P of z. So we have our solution for P of z. P of z equals a e to the kt, or kz plus b e to the minus kz. So we found there were two solutions here. We plugged in e to the RT, and then we found out after taking the square root that to get this equation to be true, r squared equals k squared, which came from putting our ansatz into our structure equation. We found that for this ansatz to work, this exponential parameter r has to be equal to plus or minus k, which is the wave number in the x direction. And so something interesting has happened here, which is that we've seen that the vertical structure in P of z is connected to the horizontal structure, which is the wave number. So the wave number tells you how long the wave crests are in the x direction. And then this structure function ends up being exponential in the vertical, but the exponential rate of decay or growth is that same thing as the wavelength in the x direction. So how quickly it changes in the vertical and how quickly it changes in the horizontal, they're connected. Okay. So we have two terms here. And now, so to determine the constants A and B, we need the boundary conditions.
Why do we use e to the kz instead of e to the kt?
Because I made a mistake over here, I'm sorry. So this equation makes no sense because it says P of z equals something that depends on time. And so that was just an error. Every single t here should be a z. I'm sorry about that. Yeah, so these are, I'm sorry. So let me correct that. Good catch. These are z. I'm too used to using this method to solve equations where the variable is time. I just forgot. Yeah. So yeah, that's right. So these are all about the vertical structure of the wave, and so the coordinate that we're using is the vertical coordinate z. Yeah, P of z does not depend on time, and so that would not make sense. But I just got lost in the sauce there. Okay. All right. So, yeah, thank you. So, we have these two constants because we had two values of r. R could either be plus k or it could be minus k. And usually when you solve a differential equation, you end up with constants. Like you either use the initial conditions to set the constants or you use the boundary conditions. In this case, we use the boundary conditions. And it turns out that one of these terms we can actually throw away right away, because we have an infinitely deep ocean, and we expect that as we go far away from the surface, as we go deeper and deeper and deeper, the wave should die out. So as z goes to negative infinity, which is deep depths, we expect the wave to die out. P of z goes to 0. So, as z goes to negative infinity, what happens to this term if k is positive? So here we'll assume k is positive. Does anyone have an idea? So if k is a positive number and we're taking z to negative infinity, what happens to this term?
0.
Goes to 0. Yeah, because you get e to the negative any larger, e to the minus 1,000. It's like some really, really small number. So this term's okay. As you go to negative infinity, that term dies out, which is what we expect. But this term, the opposite happens. Because there's this negative sign in the exponential. As z goes to negative infinity, this gets bigger and bigger and bigger. So a to the e kz goes to 0 as z goes to negative infinity. So that's okay. But b to the e minus kz goes to infinity as z goes to minus infinity. So that would be like you have a surface wave.
Oh, no. I was just...
Okay. I'm making so many mistakes when I see that look. I think it's something else. Okay, so yeah, so this term goes to infinity. So that'd be like if you have a surface wave, but then as you go deeper and deeper, the wave's just getting more and more energetic. That just doesn't really make any sense. So this term, we drop. Or we could equivalently say b equals 0. We set that coefficient to 0. So we have P of z equals a e to the k z.
So if we consider the waves going in the opposite direction, though, could we just consider the opposite case?
You mean you want to take k negative?
No, z going to positive infinity instead of negative.
So z going to positive infinity is not relevant to the system because z equals 0 is the surface of the water.
Yeah.
So, so z greater than 0 is actually in the atmosphere.
Yeah.
Right.
So would that just then simplify the system down into just the sound waves as opposed to just the surface waves?
So sound waves will never come out of this analysis, no matter what you do with it, because we've used the incompressibility condition.
Right.
So because we have du dx plus dw dz equals 0, sound waves are filtered out, they say. There's no more sound waves in the equation. Now you could ask, are you basically asking what would happen if we included the atmosphere also? We had the atmosphere and we had the ocean?
Yeah.
Yeah. So in that case, we would have two separate equations for the atmosphere and the ocean. And in the ocean version, we have to take e to the kz, and in the atmosphere version, we have to take e to the negative kz. Because there we care about the fact that the waves die out as you go infinitely high.
Yeah.
Yeah. So both of them can make sense, but in this case, we're thinking about the surface of the ocean and the depth below that, and we're just imagining the atmosphere is not really moving or whatever. But you could do a more complicated analysis that would include that, and then you might think about taking the other solution. Yeah. Does that answer your question? Okay. Okay. So we still have one coefficient left. We have this A coefficient. So, to set the coefficient A, we need the surface pressure boundary condition. So far, we've basically used the boundary condition at the deep ocean. We've said that as we get far and far away from the surface, everything has to die out. That's kind of one boundary condition. And it's called the boundary condition at infinity, because we're just measuring what happens as you get infinitely far from the surface. But we also know stuff about what happens to the wave at the actual surface, at z equals 0. So we had, at z equals 0, the pressure condition was P prime of x, z equals 0, and t equals rho naught g eta prime of x and t. And then plugging in our solution, we had P of z times sine of kx minus omega t equals rho naught g eta prime xt. And then breaking down our P of z, we had a e to the k z times sine of kx minus omega t equals rho naught g eta prime of x and t. But instead of z here, we should write 0, because so this is evaluated at z equals 0, because this is the surface condition. And so we can write that as a sine kx minus omega t equals rho naught g eta prime of x and t. Okay, and now this is where our internal solutions, so the pressure in the interior of the fluid, connects with what's happening at the free surface, because we said that there was this pressure condition, that the pressure near the surface is basically determined by how much extra water you have above your head due to the fact that the wave is fluctuating. We had this idea where we had a wave like this, and our P prime here was equal to, if this distance is eta, our P prime is rho g eta. What this tells us is that for this equation to be true, the left-hand side is the sinusoidal function of x in time, and so the right-hand side has to also be a sinusoidal function of x in time. So this tells us that eta prime of x in t is going to be eta naught of sine, I use that symbol, is going to be, I'll just use it again, eta naught sine of kx minus t. And this is the surface wave amplitude, not the background. So I'm doing a sloppy reuse of notation here where when I write here, so basically the conclusion that I'm drawing here is that we have a sinusoid equals eta prime with coefficients. So that means that eta prime must be like a sinusoid, and it has some amplitude. I'm just calling that amplitude eta naught. And now that's a bit sloppy in terms of notation because I've been using the 0 to represent the basic state, but this is conventional, so I'm just going to make this notation swap one time. And then, so we get A sine kx minus omega t equals rho naught g eta naught sine of kx minus omega t. And so we can cancel our signs, and we get A equals rho naught g eta naught. And so now at this point, and sadly we're not quite going to finish this class, so I'll just post a short video just to finish the derivation, finish the interpretation a little bit. But so we end up with, so we have solutions for p prime and eta prime. And we have eta prime of x and t equals eta naught times sine kx minus omega t, and p prime of x and z and t equals rho naught g eta naught times e to the kz times sine of kx minus omega t. Okay. And so I'm going to conclude the calculations there, but I'll just do a little bit of interpretation. So what this is said, so what's come out of our analysis so far? So we still need to calculate the dispersion relation and the wave speed formula, and that's going to be about maybe a half an hour of a YouTube lecture. What we've shown is that based on our analysis, we've shown that the surface moves like a traveling wave. So the form of the surface disturbance is very much similar to what we found for the sound wave case. It's a sinusoidal wave that's propagating in the x direction. But then the interior variables are a bit different because they have structure both in the x direction, but also in time. And how it works is that they have an x time traveling wave component, and then there's also this exponential decay, because k is positive and z is negative. So we have a traveling wave part, a traveling wave in x, and we have exponential decay in z. So our waves are going to kind of look like, if this is the amplitude of the wave, they're going to start at the surface and then they're going to get weaker and weaker as we go down. If that's something like, say, pressure, and we're graphing pressure versus depth, it's going to decay exponentially, so that when we get very far from the surface, the waves are essentially not noticeable anymore. This is true, for example, for like underwater vehicles. So if you're in a submarine or something and you're in a very, you're underneath a very violent storm, what submarines do is that they dive down deeper, because if you get to a certain depth, then even if there's very, very vigorous wave activity at the surface, if you're near the surface, that'll jostle the submarine all around and be very, very unsafe. But if you're down deep, the waves die off, and so you're no longer affected by them. So you can avoid those complications by going deeper. Okay, so my apologies for not getting this completely finished off this class. But there's just a little bit more to get the dispersion relation, and I'll discuss some interpretation. And so that should be up in the next couple of days. And then just keep your eye out on Brightspace because I'll be posting some study materials for the final exam, some practice problems, and just a topic list. Other than that, thanks for your participation throughout the class. This has been a really good group, and best of luck on all your finals. And just feel free to email me if you have any questions about the course.
Thank you. Also, I just realized the line is on the right side, or there's a drawing on the right side.